Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You recently developed a wide and deep model in TensorFlow. You generated training datasets using a SQL script that pre-processed raw data in BigQuery by performing instance-level transformations of the data. You need to create a training pipeline to retrain the model on a weekly basis. The trained model will be used to generate daily recommendations. You want to minimize model development and training time. How should you develop the training pipeline? The options are: Option A, use the Kubeflow Pipelines SDK to implement the pipeline. Use the BigQuery JobOp component to run the pre-processing script and the custom training JobOp component to launch a Vertex AI training job. Option B, use the Kubeflow Pipelines SDK to implement the pipeline. Use the Dataflow Python JobOp component to pre-process the data and the custom training JobOp component to launch a Vertex AI training job. Option C, use the TensorFlow Extended SDK to implement the pipeline. Use the example gen component with the BigQuery executor to ingest the data, the transform component to pre-process the data, and the trainer component to launch a Vertex AI training job. Option D, use the TensorFlow Extended SDK to implement the pipeline. Implement the pre-processing steps as part of the input_fn of the model. Use the example gen component with the BigQuery executor to ingest the data and the trainer component to launch a Vertex AI training job.
To arrive at the correct answer, we focus on the keywords: generated training datasets using a SQL script, pre-processed raw data in BigQuery, minimize model development and training time.
The correct answer is Option A, use the Kubeflow Pipelines SDK to implement the pipeline. Use the BigQuery JobOp component to run the pre-processing script and the custom training JobOp component to launch a Vertex AI training job.
Why is this correct? A. Using Kubeflow pipelines with BigQuery JobOp reuses the existing SQL script, minimizing development time. Custom training JobOp efficiently trains the TensorFlow model on Vertex AI. Why are the others incorrect? B. Dataflow Python JobOp would require rewriting the existing SQL script into Python for Dataflow, which increases model development time unnecessarily. C. The TFX transform component requires rewriting the SQL pre-processing logic using TF transform, increasing development time compared to reusing the existing SQL script. D. Implementing pre-processing in the input_fn adds computational overhead during training, increasing training time, and requires rewriting the existing SQL logic.
You built a custom ML model using scikit-learn. Training time is taking longer than expected. You decide to migrate your model to Vertex AI training, and you want to improve the model's training time. What should you try out first? The options are: Option A, train your model in a distributed mode using multiple compute engine VMs. Option B, train your model using Vertex AI training with CPUs. Option C, migrate your model to TensorFlow and train it using Vertex AI training. Option D, train your model using Vertex AI training with GPUs.
To arrive at the correct answer, we focus on the keywords: scikit-learn, improve the model's training time, first.
The correct answer is Option B, train your model using Vertex AI training with CPUs.
Why is this correct? B. Scikit-learn models natively run on CPUs and do not support GPUs out of the box. Provisioning a more powerful CPU instance in Vertex AI training is the simplest and first step to reduce training time without code changes. Why are the others incorrect? A. Scikit-learn does not natively support distributed multi-node training, making this approach too complex to be the first step to try. C. Rewriting the entire model in TensorFlow requires significant development effort in code modification, which should not be the first approach to try. D. Standard scikit-learn does not utilize GPU acceleration natively, so using GPUs will increase costs without improving the training time.
You are a data scientist at an industrial equipment manufacturing company. You are developing a regression model to estimate the power consumption in the company's manufacturing plants based on sensor data collected from all of the plants. The sensors collect tens of millions of records every day. You need to schedule daily training runs for your model that use all the data collected up to the current date. You want your model to scale smoothly and require minimal development work. What should you do? The options are: Option A, develop a custom TensorFlow regression model and optimize it using Vertex AI training. Option B, develop a regression model using BigQuery ML. Option C, develop a custom scikit-learn regression model and optimize it using Vertex AI training. Option D, develop a custom PyTorch regression model and optimize it using Vertex AI training.
To arrive at the correct answer, we focus on the keywords: regression model, tens of millions of records every day, schedule daily training runs, scale smoothly and require minimal development work.
The correct answer is option B, develop a regression model using BigQuery ML.
Why is this correct? The BigQuery ML enables you to build and schedule machine learning models directly where the data resides using SQL, satisfying the need for smooth scaling and minimal development work for large datasets. Why are the others incorrect? A. Developing a custom TensorFlow model requires writing custom training code and setting up pipelines, which violates the requirement for minimal development work. C. Building a custom scikit-learn model demands additional effort for distributed training on tens of millions of records, failing the minimal development work and smooth scaling requirements. D. Creating a custom PyTorch model involves significant coding and infrastructure management, conflicting with the goal of achieving minimal development work.
You recently developed a deep learning model. To test your new model, you trained it for a few epochs on a large dataset. You observe that the training and validation losses barely changed during the training run. You want to quickly debug your model. What should you do first? The options are: Option A, verify that your model can obtain a low loss on a small subset of the dataset. Option B, add handcrafted features to inject your domain knowledge into the model. Option C, use the Vertex AI hyperparameter tuning service to identify a better learning rate. Option D, use hardware accelerators and train your model for more epochs.
To arrive at the correct answer, we focus on the keywords: deep learning model, training and validation losses barely changed, quickly debug your model, first.
The correct answer is option A, verify that your model can obtain a low loss on a small subset of the dataset.
Why is this correct? A. Overfitting a small batch is a standard first step in debugging deep learning models. If the model cannot overfit a few examples, there is likely a fundamental bug in the architecture or data pipeline. Why are the others incorrect? B. Adding handcrafted features increases complexity and does not help identify fundamental bugs in the model architecture or pipeline, which is the immediate concern. C. Hyperparameter tuning on a large dataset is time-consuming and expensive. It should be done only after verifying that the model is capable of learning on a small subset. D. Training for more epochs wastes compute resources if the model has a fundamental bug preventing it from learning, as indicated by the unchanged losses.
You are working on a system log anomaly detection model for a cybersecurity organization. You have developed the model using TensorFlow, and you plan to use it for real-time prediction. You need to create a Dataflow pipeline to ingest data via pub/sub and write the results to BigQuery. You want to minimize the serving latency as much as possible. What should you do? The options are: Option A, containerize the model prediction logic in Cloud Run, which is invoked by Dataflow. Option B, load the model directly into the Dataflow job as a dependency, and use it for prediction. Option C, deploy the model to a Vertex AI endpoint, and invoke this endpoint in the Dataflow job. Option D. Deploy the model in a TF serving container on Google Kubernetes Engine, and invoke it in the Dataflow job.
To arrive at the correct answer, we focus on the keywords, real-time prediction, Dataflow pipeline, minimize the serving latency as much as possible.
The correct answer is option B, load the model directly into the Dataflow job as a dependency, and use it for prediction.
Why is this correct? B. Loading the model directly into the Dataflow job minimizes serving latency by eliminating the network overhead associated with making remote API calls for prediction. Why are the others incorrect? A. Invoking an external cloud run service for each prediction introduces network communication overhead, which increases serving latency. C. Calling an external Vertex AI endpoint adds network latency to the prediction process, failing to minimize latency as much as possible. D. Making network calls to a remote TF serving container on GKE adds unnecessary network latency compared to local, in-memory predictions.
You are a data scientist at an industrial equipment manufacturing company. You are developing a regression model to estimate the power consumption in the company's manufacturing plants based on sensor data collected from all of the plants. The sensors collect tens of millions of records every day. You need to schedule daily training runs for your model that use all the data collected up to the current date. You want your model to scale smoothly and require minimal development work. What should you do? The options are: Option A, train a regression model using AutoML tables. Option B, develop a custom TensorFlow regression model and optimize it using Vertex AI training. Option C, develop a custom scikit-learn regression model and optimize it using Vertex AI training. Option D, develop a regression model using BigQuery ML.
To arrive at the correct answer, we focus on the keywords, tens of millions of records every day, schedule daily training runs, scale smoothly, require minimal development work.
The correct answer is option D, develop a regression model using BigQuery ML.
Why is this correct? D. BigQuery ML allows building and training models directly where massive datasets reside using standard SQL. It handles scaling automatically without infrastructure management and integrates easily with scheduled queries for daily retraining, perfectly satisfying the requirement for minimal development work. Why are the others incorrect? A. While AutoML requires minimal coding, it is not optimized or cost-effective for daily retraining on massive, continually growing datasets, tens of millions of records daily, compared to the seamless in-place capabilities of BigQuery ML's. B. Developing a custom TensorFlow model requires substantial development and maintenance effort to handle data pipelines, training scripts, and infrastructure scaling, which directly contradicts the requirement for minimal development work. Why are the others incorrect? C. Building a custom scikit-learn model demands significant development work for pipeline management. Furthermore, scikit-learn does not natively scale out to tens of millions of daily records as smoothly as BigQuery ML.
You need to train a natural language model to perform text classification on product descriptions that contain millions of examples and 100,000 unique words. You want to pre-process the words individually so that they can be fed into a recurrent neural network. What should you do? The options are: Option A, create a hot encoding of words and feed the encodings into your model. Option B, identify word embeddings from a pre-trained model and use the embeddings in your model. Option C, sort the words by frequency of occurrence and use the frequencies as the encodings in your model. Option D, assign a numerical value to each word from 1 to 100,000 and feed the values as inputs in your model.
To arrive at the correct answer, we focus on the keywords, text classification, millions of examples, 100,000 unique words, recurrent neural network.
The correct answer is option B, identify word embeddings from a pre-trained model, and use the embeddings in your model.
Why is this correct? B. Pre-trained word embeddings provide dense representations that capture semantic meaning efficiently, which is ideal for a large vocabulary of 100,000 words fed into an RNN, avoiding the sparsity of one-hot encoding. Why are the others incorrect? A. One-hot encoding creates extremely sparse, high-dimensional vectors, 100,000 dimensions, that are computationally expensive and fail to capture semantic relationships between words. C. Sorting by frequency and using frequencies as encodings does not provide unique, meaningful representations for individual words suitable for sequence modeling in an RNN. D. Assigning a single numerical value to each word implies an ordinal relationship that does not exist in language, confusing the neural network.
You need to execute a batch prediction on 100 million records in a BigQuery table with a custom TensorFlow DNN regressor model, and then store the predicted results in a BigQuery table. You want to minimize the effort required to build this inference pipeline. What should you do? The options are: Option A, import the TensorFlow model with BigQuery ML, and run the milliliter predict function. Option B, use the TensorFlow BigQuery reader to load the data, and use the BigQuery API to write the results to BigQuery. Option C, create a Dataflow pipeline to convert the data in BigQuery to TF records. Run a batch inference on Vertex AI prediction, and write the results to BigQuery. Option D, load the TensorFlow saved model in a Dataflow pipeline. Use the BigQuery I/O connector with a custom function to perform the inference within the pipeline, and write the results to BigQuery.
To arrive at the correct answer, we focus on the keywords: batch prediction, BigQuery table, custom TensorFlow DNN regressor model, store the predicted results in a BigQuery table, minimize the effort.
The correct answer is option A, import the TensorFlow model with BigQuery ML, and run the milliliter predict function.
Why is this correct? A. BigQuery ML supports importing custom TensorFlow models to perform batch predictions directly on data stored in BigQuery using ml.predict, which minimizes effort by eliminating data movement and external infrastructure. Why are the others incorrect? B. Manually extracting data to run predictions externally and writing results back to BigQuery requires custom scripting and data movement, significantly increasing effort. C. Building a Dataflow pipeline, converting data to TF records, and managing Vertex AI prediction adds unnecessary infrastructure complexity and effort. D. Creating and maintaining a custom Dataflow pipeline with BigQuery I/O for inference is far more complex and requires more effort than using native BigQuery ML.
You are working on a classification problem with time series data. After conducting just a few experiments using random cross-validation, you achieved an area under the receiver operating characteristic curve, AUC-ROC, value of 99% on the training data. You haven't explored using any sophisticated algorithms or spent any time on hyperparameter tuning. What should your next step be to identify and fix the problem? The options are: Option A, address the model overfitting by using a less complex algorithm and use k-fold cross-validation. Option B, address data leakage by applying nested cross-validation during model training. Option C, address data leakage by removing features highly correlated with the target value. Option D, address the model overfitting by tuning the hyperparameters to reduce the AUC-ROC value.
To arrive at the correct answer, we focus on the keywords: time series data, random cross-validation, value of 99%, fix the problem.
The correct answer is option B, address data leakage by applying nested cross-validation during model training.
Why is this correct? B. Time series data requires chronological ordering. Random cross-validation causes data leakage by using future data to predict the past. Nested or time series cross-validation respects temporal order, preventing leakage and providing realistic performance estimates. Why are the others incorrect? A. Standard k-fold cross-validation randomly partitions data, ignoring the temporal sequence of time series data. This fails to resolve the underlying data leakage problem, causing the unrealistically high AUC-ROC. C. While removing highly correlated features is a general technique, it does not fix the root cause here, data leakage from ignoring the temporal nature of the data during cross-validation. D. Deliberately tuning hyperparameters to worsen the model's performance does not solve the fundamental validation flaw causing data leakage in time series data.
You are using Kubeflow pipelines to develop an end-to-end PyTorch-based MLOps pipeline. The pipeline reads data from BigQuery, processes the data, conducts feature engineering, model training, model evaluation, and deploys the model as a binary file to cloud storage. You are writing code for several different versions of the feature engineering and model training steps, and running each new version in Vertex AI pipelines. Each pipeline run is taking over an hour to complete. You want to speed up the pipeline execution to reduce your development time, and you want to avoid additional costs. What should you do? The options are: Option A, comment out the part of the pipeline that you are not currently updating. Option B, enable caching in all the steps of the Kubeflow pipeline. Option C, delegate feature engineering to BigQuery and remove it from the pipeline. Option D, add a GPU to the model training step.
To arrive at the correct answer, we focus on the keywords: Kubeflow pipelines, writing code for several different versions, speed up the pipeline execution, avoid additional costs.
The correct answer is option B, enable caching in all the steps of the Kubeflow pipeline.
Why is this correct? B. Enabling caching prevents the re-execution of pipeline steps whose inputs and code have not changed. This significantly speeds up iterations during development and saves compute costs. Why are the others incorrect? A. Commenting out parts of the pipeline can break downstream dependencies in the end-to-end flow, making it an error-prone and tedious manual workaround. C. Delegating feature engineering to BigQuery requires rewriting the pipeline code and does not necessarily speed up development iterations or guarantee avoided costs. D. Adding a GPU to the model training step increases compute expenses, which directly violates the requirement to avoid additional costs.
You are creating an ML pipeline for data processing, model training, and model deployment that uses different Google Cloud services. You have developed code for each individual task, and you expect a high frequency of new files. You now need to create an orchestration layer on top of these tasks. You only want this orchestration pipeline to run if new files are present in your dataset in a cloud storage bucket. You also want to minimize the compute node costs. What should you do? The options are: Option A, create a pipeline in Vertex AI pipelines. Configure the first step to compare the contents of the bucket to the last time the pipeline was run. Use the Scheduler API to run the pipeline periodically. Option B, create a cloud function that uses a cloud storage trigger and deploys a Cloud Composer directed acyclic graph (DAG). Option C, create a pipeline in Vertex AI pipelines. Create a cloud function that uses a cloud storage trigger and deploys the pipeline. Option D, deploy a Cloud Composer directed acyclic graph (DAG) with a GCS object update sensor class that detects when a new file is added to the cloud storage bucket.
To arrive at the correct answer, we focus on the keywords: ML pipeline, orchestration layer, only want this orchestration pipeline to run if new files are present, cloud storage bucket, minimize the compute node costs.
The correct answer is option C, create a pipeline in Vertex AI pipelines. Create a cloud function that uses a cloud storage trigger and deploys the pipeline.
Why is this correct? C. Vertex AI pipelines provide serverless orchestration, minimizing costs. A cloud function with a cloud storage trigger efficiently initiates the pipeline only when new files arrive, satisfying the event-driven requirement. Why are the others incorrect? A. Running periodically with a scheduler wastes compute resources to check for new files, instead of running strictly when new files arrive. B. Cloud Composer requires a constantly running cluster with always-on compute nodes, which does not minimize compute costs compared to serverless options. D. Cloud Composer relies on always-on infrastructure, and running a sensor continuously consumes resources, contradicting the requirement to minimize compute node costs.
You work for a company that is developing an application to help users with meal planning. You want to use machine learning to scan a corpus of recipes and extract each ingredient, e.g., carrot, rice, pasta, and each kitchen cookware, e.g., bowl, pot, spoon, mentioned. Each recipe is saved in an unstructured text file. What should you do? The options are: Option A. Create a text dataset on Vertex AI for entity extraction. Create two entities called ingredient and cookware, and label at least 200 examples of each entity. Train an AutoML entity extraction model to extract occurrences of these entity types. Evaluate performance on a holdout dataset. Option B. Create a multi-label text classification dataset on Vertex AI. Create a test dataset, and label each recipe that corresponds to its ingredients and cookware. Train a multi-class classification model. Evaluate the model's performance on a holdout dataset. Option C. Use the entity analysis method of the natural language API to extract the ingredients and cookware from each recipe. Evaluate the model's performance on a pre-labeled dataset. Option D. Create a text dataset on Vertex AI for entity extraction. Create as many entities as there are different ingredients and cookware. Train an AutoML entity extraction model to extract those entities. Evaluate the model's performance on a holdout dataset.
To arrive at the correct answer, we focus on the keywords: extract each ingredient, each kitchen cookware, unstructured text file.
The correct answer is option A. Create a text dataset on Vertex AI for entity extraction. Create two entities called ingredient and cookware, and label at least 200 examples of each entity. Train an AutoML entity extraction model to extract occurrences of these entity types. Evaluate performance on a holdout dataset.
Why is this correct? A. Vertex AI text entity extraction is ideal for locating specific items within unstructured text. Training an AutoML model with custom ingredient and cookware entities correctly addresses this domain-specific extraction requirement. Why are the others incorrect? B. Multi-label classification categorizes the entire document, which fails to extract the specific occurrences of individual ingredients and cookware from the text. C. The natural language API entity analysis extracts predefined general entities and is not tailored to recognize domain-specific categories like ingredients or cookware. D. Creating a distinct entity for every possible ingredient or cookware item is highly inefficient and unscalable compared to using broad entity categories.
You are developing a natural language processing model that analyzes customer feedback to identify positive, negative, and neutral experiences. During the testing phase, you notice that the model demonstrates a significant bias against certain demographic groups, leading to skewed analysis results. You want to address this issue following Google's responsible AI practices. What should you do? The options are: Option A. Use Vertex AI's model evaluation low assess bias in the model's predictions, and use post-processing to adjust outputs for identified demographic discrepancies. Option B. Implement a more complex model architecture that can capture nuanced patterns in language to reduce bias. Option C. Audit the training dataset to identify underrepresented groups and augment the dataset with additional samples before retraining the model. Option D. Use Vertex Explainable AI to generate explanations and systematically adjust the predictions to address identified biases.
To arrive at the correct answer, we focus on the keywords: bias against certain demographic groups. Address this issue following Google's responsible AI practices.
The correct answer is option C. Audit the training dataset to identify underrepresented groups and augment the dataset with additional samples before retraining the model.
Why is this correct? C. Google's responsible AI practices emphasize mitigating bias at the source. Auditing the training data for representativeness and augmenting it addresses the root cause of the bias before retraining the model. Why are the others incorrect? A. Post-processing predictions is a reactive approach and doesn't fix the underlying cause of the bias. Google's practices recommend addressing bias in the data or model architecture itself. B. Increasing model complexity does not guarantee a reduction in bias, it may even amplify existing biases if the training dataset remains skewed. D. Explainable AI helps understand feature attribution, but adjusting predictions manually is not a scalable or principled way to fix root cause data bias according to responsible AI guidelines.
You work at a retail company and are tasked with developing an ML model to predict product sales. Your company's historical sales data is stored in BigQuery and includes features such as date, store location, product category, and promotion details. You need to choose the most effective combination of a BigQuery ML model and feature engineering to maximize prediction accuracy. What should you do? The options are: Option A, use a linear regression model. Perform one-hot encoding on categorical features, and create additional features based on the date, such as day of the week or month. Option B, use a boosted tree model. Perform label encoding on categorical features, and transform the date column into numeric values. Option C, use an autoencoder model. Perform label encoding on categorical features, and normalize the date column. Option D, use a matrix factorization model. Perform one-hot encoding on categorical features, and create interaction features between the store location and product category variables.
To arrive at the correct answer, we focus on the keywords: predict product sales, BigQuery, date, store location, product category, feature engineering.
The correct answer is option A, use a linear regression model. Perform one-hot encoding on categorical features, and create additional features based on the date, such as day of the week or month.
Why is this correct? A. Linear regression is well suited for predicting continuous numeric values like sales. One-hot encoding correctly represents categorical data without implying false ordinality, and creating specific date features like day or month captures seasonal trends essential for accurate sales forecasting. Why are the others incorrect? B. Label encoding categorical variables introduces false ordinal relationships, which can degrade model performance. Additionally, merely converting dates to numeric values fails to capture crucial cyclical or seasonal patterns. C. Autoencoders are unsupervised learning models primarily used for dimensionality reduction or anomaly detection. They are not appropriate for supervised regression tasks such as predicting product sales. Why are the others incorrect? D. Matrix factorization is designed for collaborative filtering and recommendation systems. It is not suitable for predicting continuous sales figures using diverse categorical and temporal features.
You work for a small company that has deployed an ML model with auto-scaling on Vertex AI to serve online predictions in a production environment. The current model receives about 20 prediction requests per hour with an average response time of 1 second. You have retrained the same model on a new batch of data, and now you are canary testing it, sending 10% of production traffic to the new model. During this canary test, you notice that prediction requests for your new model are taking between 30 and 180 seconds to complete. What should you do? The options are: Option A, submit a request to raise your project quota to ensure that multiple prediction services can run concurrently. Option B, turn off auto-scaling for the online prediction service of your new model. Use manual scaling with one node always available. Option C, remove your new model from the production environment. Compare the new model and existing model codes to identify the cause of the performance bottleneck. Option D, remove your new model from the production environment. For a short trial period, send all incoming prediction requests to BigQuery. Request batch predictions from your new model, and then use the data labeling service to validate your model's performance before promoting it to production.
To arrive at the correct answer, we focus on the keywords: autoscaling, average response time of 1 second, retrained the same model, canary testing it, taking between 30 and 180 seconds to complete.
The correct answer is option C. Remove your new model from the production environment. Compare the new model and existing model codes to identify the cause of the performance bottleneck.
Why is this correct? C. The canary test revealed a severe performance degradation. The new model must be immediately removed from production to protect user experience, and its code and configuration must be compared to the existing model to identify the root cause of the bottleneck. Why are the others incorrect? A. Project quota limits generally lead to rejected or failed requests rather than significantly increasing the latency of successful prediction requests. B. While low canary traffic might cause autoscaling cold starts, forcing manual scaling circumvents the problem rather than investigating if the retrained model itself contains an inherent performance bottleneck. D. Routing requests to BigQuery and using data labeling service helps evaluate model accuracy and prediction quality, but does not diagnose or resolve performance bottlenecks or response latency.